In this video, we're looking at an improper integral. So it's the integral of 1 over x minus 1 integrated on -4 to 4. And the main point of this video is to compare two different approaches to computing this integral. So we have what I would call the standard approach, and that's where we split the integration interval at the problematic point, that's x equals 1, where the denominator vanishes here and where we see a vertical asymptote in the graph. And then each of those integrals is an improper integral, and we evaluate each of those improper integrals. And actually what happens here is each of those diverges, and then we're forced to say the integral diverges. Well, there's a better answer, and this is called the Cauchy Principal Value of the integral. I see the function diving to negative infinity from the left and to positive infinity from the right, but it's doing this at exactly the same rate from the left and right. So those positive and negative areas should still cancel each other out, and we should still get a finite value for the area of this function. The way we're going to accomplish this is by dealing with the limit as we get close to the problematic point in a symmetric way. So we're going to re-express the integral as I've shown in the setup for the question here. And what we're doing is integrating all the way to this point, 1 minus epsilon to the left of the problematic point. And then our second integral goes from 1 plus epsilon all the way to the terminating point at x equals 4. By dealing with the limits symmetrically, things are going to simplify before we take the limit as epsilon goes to 0, and we'll get a more meaningful answer for this integral. So let's get into the actual work of the problem. First, we want to show that the standard approach results in a divergent integral. And so the standard approach is to split the integration interval at the problematic point x equals 1, and then subbing in x equals 1 is problematic in both of these expressions. So the integrand is not defined at x equals 1 for either one of these. So we replace that 1 with, for example, a t, and then we take the limit as t approaches 1. So for the first integral, t is going to be approaching 1 from the left. In the second integral, t is approaching 1 from the right. And now we're able to evaluate our integrals before we take the limits. This integrates to the natural log absolute value x minus 1. And we're evaluating that on -4 to t. Same antiderivative in the second one. And we're evaluating from t to 4. Got to fix the sign error there. And now we sub in our limits of integration. And so in my first limit, I have a natural log absolute value t minus 1 minus natural log absolute value -4 minus 1. And the absolute value of -5 is just 5. So I have minus natural log 5. And then I have my second limit. This starts with a natural log absolute value 4 minus 1, which is just natural log 3, and then minus natural log absolute value t minus 1. And that second limit is t goes to 1 from the right. Then these constants, natural log 3 and natural log 5, they could just come out of the limits if you want. And the interesting part is the limits of these natural logs as their arguments become closer and closer to 0. So the first one is the limit as t goes to 1 from the left, natural log absolute value t minus 1. And as t is getting very close to 1 there, the argument of the natural log function is getting very close to 0. And we know what happens to the natural log at 0. It blows up to negative infinity. In our second limit, we have the limit as t approaches 1 from the right of the negative of the natural log of the absolute value of t minus 1. And again, the argument of the natural log function there is getting arbitrarily close to 0. So the natural log gives us a limit of negative infinity, but there was a minus sign out in front of it. And that gives us plus infinity. Now, the problem with the standard approach to these integrals, and what I mean is the way it's normally taught in Calculus 2, is that we're taught if any one of the individual integrals in one of these problems diverges, in other words, goes to an infinite result, then we have to say the entire thing diverges. And you might argue, well, there's a negative infinity plus an infinity here, and don't those just add up to 0? And it's not that simple. They would only add up to 0 if each of those infinities is happening in a perfectly symmetric way. So we're stuck just sort of throwing up our hands and saying this integral diverges and we're done. We can't get the area bounded by this thing. And this, of course, is where the Cauchy Principal Value comes to the rescue. We do have divergence happening in a symmetric way on the left and right sides of this problematic point. So let's take the Cauchy Principal Value approach to this thing and see if we can get a more meaningful answer. So back to our original integral, we have the integral from -4 to 4 of 1 over x minus 1 dx. X equals 1 is the problematic point where the denominator vanishes. And now we're going to handle this limiting process at the problematic point in a symmetric way. So epsilon is just some small positive number. That means 1 minus epsilon is very slightly to the left of the problematic point. And my first integral is going to add up all the area until we get really close to the problematic point from the left. In my second integral, I add up all the area from really close to the problematic point, but to the right of it, all the way to the terminating value for this definite integral at x equals 4. And after all that is cleaned up, then we're going to take the limit, and that's the limit as epsilon goes to 0. And so the antiderivatives are familiar. Each of these just integrates to the natural log absolute value x minus 1. And when I plug in 1 minus epsilon to this first one, it gives me a 1 minus epsilon minus 1. In other words, the natural log of the absolute value of negative epsilon. And because epsilon is a positive number, the absolute value is going to erase that minus sign. Then I'm subtracting the natural log of the absolute value of negative 5, which is going to give me the natural log of 5. In my second piece, I sub in the upper limit, and I get the natural log absolute value of 3, or just natural log 3. And in my lower limit, I'm subtracting that. I get the natural log absolute value of 1 plus epsilon minus 1, which is just natural log absolute value of epsilon. And because epsilon is positive, the absolute value bars aren't doing anything there. So just to make the algebra exceptionally clear, my first natural log term, when I apply the absolute value, it becomes natural log epsilon. And then I have minus log 5 plus log 3 minus a natural log epsilon. And this is where the magic happens. Those natural log epsilons are going to cancel out. There are no more epsilons left in the limit. And so when I apply this limit, I just get natural log 3 minus natural log 5. And that's called the Cauchy Principal Value for the integral, and it's probably a more meaningful interpretation of the area bounded by this curve. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.